Right, good morning, everyone. Let's begin with homework 13. If you have any questions, let's handle those questions. How many of you have already submitted homework 13? Okay, how many of you are working on homework 13? How many of you have not opened homework 13? All right, any questions about homework 13? I covered pretty much all questions last class. Before I move on, I just want to make sure all questions are answered. Okay. Let's see. Control 1. All right. Assignments, yes. You mean like entering the data in the problem, or is it just concept? Okay, so the question being asked is about how does voltage or current relate with time? And power, okay. So simply stated, if it's V of t or I of t or P of t, it simply means that that quantity is a function of time. And again, to simply state it, the function of time simply means at any given point in time, the value could be different. That's all it means. Doesn't mean anything else. So if you have V of t, and V of t simply means voltage, either for the capacitor or the inductor or for any quantity as a function of time. So voltage for the capacitor could be different at different point in time. And when we plot out these quantities, let's go to the notebook. When we plot out these quantities, it could be a straight line, it could be any kind of waveform depending on the values. So let's take DC for example. If you have a DC voltage, just time on the x-axis, this time could be, the unit of course is seconds, but it could be milliseconds, microseconds, nanoseconds, could be anything. If we say we wish to plot the value of a DC voltage or current, and here's 0. 0 simply means the point at which we begin our analysis, the point at which we are trying to identify with the system, right? So 0 in this case, in the time axis, simply means from the time we begin our analysis. Actual time could be anything. Could be 9 a.m., could be 10 p.m., doesn't really matter. But the point at which we begin analysis of a system, that's time equal to 0. So this could be V of t or I of t or P of t. Voltage, current, or power as a function of time. If it's DC voltage or current, let's say 5 volts DC, that at any given point in time, it'll have the exact same value. So if it's at 1 second or 2 seconds or 3 seconds, 4, 5, 6, 7 seconds, it'll have the same value of 5 volts. So it's constant. If it's any other value for like a capacitor or inductor, it could change, whether it's AC, whether it's DC, or is it just random. I'm just going to draw out some random. It could have a value of, let's say, 0, 1, 2, 3, 4, 5, 6, 7. Could have a value here, 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 and here. And when we join the dots together, we'd get like a waveform. But that's all it means. It doesn't mean anything else. Voltage as a function of time, meaning it has a different value at any given point in time. When we get to AC analysis, we'll work with sinusoidal waveforms, which is the shape of the power outlets, shape of the voltage of the power outlets, which is something like this. So at any given point in time, it has different values. Right? It has different values at any given point in time. You could break this up into, let's say, if this was the waveform or the value of the voltage over 1 second, we could break up that 1 second into 100 parts. And we'd say at 0.1 second, it has a value of this. At 0.2 seconds, it has a different value. 0.3 seconds, it has a different value. And if we wish to analyze the system between, let's say, 0 and 0.5 seconds, it has a different value at every point. 100 parts would be 0.01, sorry. 10 parts would be 0.1. But it doesn't matter. We could break it up into 1,000 parts. You'd say it's 1 millisecond and analyze the system for the first 5 milliseconds. And then again, you'd have a different value as a function of time. That's all it means. Does that answer your question? Somewhat. Mm-hmm. Mm-hmm. So this one, current through a 0.5 microfarad capacitor is shown in the figure, which is kind of like a square wave with a gap in the middle. Okay. So mm-hmm. Okay, I is equal to C dV over dt. So you're trying to find the voltage. So have you, so here are all the annotated slides. And the last one right here. So you see these annotated notes. So in chapter 3, slide number or page number 27, it shows all the mathematical equations for both the inductor and the capacitor. And so at that point, it is just simply math. V of t is given to us. We describe it for that specific time period between 0 and 1. So we'd have to break it down. So we write 3 equations. So for this one, current I is given. So I has a value of 20 milliamps for the first 2 milliseconds. Okay, so we write an equation. We don't even have to write an equation. It's a flat line. So it's a constant. So current I is constant value of 20 for the first 2 milliseconds. And then it's minus 20 for 3 to 5. So the, another 2 milliseconds, it's minus 20. And between 2 and 3 for 1 millisecond time period, it's 0. Simply take the derivative, not derivative, sorry, integrate. Since it's voltage is the integral of the current. We simply plug in values right here in this equation. So V of t, in this case, would be 20, sorry, not V of t. I of t would be 20, 0, and minus 20. And we simply plug these three values in this equation to find those corresponding voltage values. Inductance, simply the value of the inductor. Oh, sorry, that's for the inductor. And plug it into here. Yeah. So yeah, the lecture videos cover all of this. It does cover the explanation. What is VFT, what is IFT, how to use the equations, and what does it mean time t equals 0 and the residual charge that's present in the inductor or capacitor, and how we add. Does that make sense? Other questions? That's it? Okay. Any other questions from anyone? Okay. Let's go to transients. Okay. Transients, if you have not yet taken a look at the videos, I'll explain. Transient means fleeting, right? It's momentary. Just the word itself means momentary. It's fleeting. So transient response refers to the energy transfer portion between a source and the inductor or capacitor. Okay. So resistors are not energy storage devices. Inductors and capacitors are energy storage devices. So when you have a source in a circuit and you're sending energy into an inductor or capacitor, that energy transfer takes some time. Okay, it does not take place in an instant. Thanos cannot snap his fingers and have all the energy dissipated in the universe all at once. It doesn't happen. Okay, it takes a finite amount of time for the energy to be transferred from the source into the inductor or capacitor. And then when a situation reverses, the energy is released back into the circuit. That also takes a finite amount of time. It could be nanoseconds, milliseconds, multiple seconds, but it takes a finite amount of time. Okay. And the time from when the energy is transferred into the capacitor, meaning the energy is into the capacitor or inductor, meaning the energy is now being built up in these components. That is known as charging of the capacitor or charging of the inductor. And when the energy is released back into the circuit, meaning the energy storage elements are releasing the energy, so they're going back towards 0, that is known as the discharging phase. This charging and discharging phase, the response of the voltage and current during this phase is known as the transient response. And so we derive equations to describe the voltage and current during this charging and discharging phase. And that is known as the transient response. So based on the inductor and the capacitor, and based on the charging and discharging, we have 4 different kinds of responses, right? Charging and discharging of capacitor, charging and discharging of the inductor. Okay, and so there's 4 different kinds of equations. However, there's one general equation that you can use to describe everything. I can copy out that slide right there. Let's go to chapter 4 and look at this slide right here. This is known as the general solution for the natural and step response. If you have not yet taken a look at the videos, please do so. Step response is basically charging, and natural response is discharging. Okay. The step response is also known as the forced response. It is not as sinister as the word sounds. Forced simply means that there's an external energy source that is prompting a response from the capacitor or inductor, which is basically every single circuit that you have talked about. Like a resistor, capacitor, or inductor does not have any energy of its own. We always have an external voltage source or a current source that supplies energy and that elicits a response from these components, right? We apply a voltage to a resistor, it causes energy to be transferred. If you apply current to a resistor, again, it causes energy to be transferred. So just in itself, everything is a forced response. Does that make sense to everyone? Okay. So again, it's not as sinister as the word forced sounds. The forced response or the step response is simply the application of voltage or current. And the natural response is basically there is no source present in the system anymore. It is just the capacitor or inductor that is releasing the circuit. That is releasing the stored energy. Since there is no external energy source, it's known as a natural response. That's what it means. So this one equation describes the natural and the step response, meaning the charging as well as the discharging for both capacitors and inductors. So let's take a pause. You look at the equation, and then I'll answer questions, and I'll just explain what this equation means. Okay. How many of you have already started watching the lecture videos on this? Okay. All right. So since it's pretty much a blank slate, let me start from the top. Actually, let's go here. Yeah. Okay, so we spoke about charging and discharging, right? For capacitor and inductor. For me, there's beauty in this, and it's this is unique, and it's also the same. No matter the size of the capacitor, no matter the conditions in the circuit, no matter what the component is, whether it's a capacitor or inductor, that charging and discharging follows the exact same pattern. It is exponential. It is exponential in nature. And it's one of the things that's just is. I guess it's natural laws of physics. So if you're charging, whether it's a capacitor or inductor, you have an exponential curve that is going up, inductor and capacitor. L is inductor, C is capacitor. And discharging also applies to both inductor and capacitor. Okay. So this is the form that has been observed no matter what the circuit is, no matter what the component is, whether it's inductor, capacitor, whether it's charging or discharging, it is always exponential in nature, and it always follows this pattern. Okay, yes. So a question being asked is, what is the purpose of an inductor and a capacitor in a circuit? The answer is kind of broad. You could build a circuit without a capacitor or inductor. The applications are multivariate. You all use it every single day. All of the touchscreens that we use in modern electronic devices, they're all capacitive touchscreens. So when we touch our fingers onto the surface of this touchscreen, there's a digitizer on there, there's a sensor on there. And what it does is it measures capacitance across the surface of the touchscreen. And with our fingers, when we touch it, it changes the capacitance that is measured. And depending on, well, depending on the spot, of course, the sensor or the circuit realizes at what point the capacitance has changed, and then translates that into position, X and Y. Before capacitive touchscreens, we had resistive touchscreens. Resistive touchscreens, you'd have to, I don't know if you've ever used resistive touchscreens. I have. I actually have devices with resistive touchscreens, but a finger tap would not work. You'd have to actually push down, force. And the reason is because it's measuring the change in the resistance by measuring the change, by measuring the force that is applied to that screen. And so resistive touchscreens work better when you'd have like sharp devices and you'd actually have a pinpoint that would be more accurate. And so the older kind of touchscreens used to have like a stylus to use them. And so this is by far the most common application for capacitor in modern day. But there are many other places where we use capacitors. In all power supplies, whether it's laptop adapters or mobile phone chargers, desktops, monitors, capacitors, you do the function of filtering out AC ripples. So when we convert AC to DC, capacitors are used to store the energy, and in the negative half cycle of an AC supply, the capacitor releases that stored energy back into the circuit. And so it creates a nice, flat, smooth waveform. So that's another thing. One of the other real-life applications, when I say real life, all of the applications are real life, but something that consumers can, use is in camera flash. Not the ones that are on our smartphones, but the actual camera flash that's on a, let's say like an SLR, DSLR cameras that you mount on top of professional cameras. You may have not used one, but you may have certainly seen one, right? If you have ever used one, when you mount it on top, you'd have like 4 AA batteries or something that goes inside these cameras. And every time you click the shutter button or you press the shutter, it sends a signal via a couple of connections on top of the camera, and it tells the flash to activate. What it is doing is it's releasing all of that energy all at once, so that that light bulb in there just flashes momentarily. And then you'd hear sort of a whirring noise, like, and what that sound is, it's taking that energy from the batteries and it's charging up that capacitor. And so it charges up that capacitor. The capacitor stores that energy. When you click the shutter button, it releases that energy all at once. So the camera flash is another application there. So if you can get hold of a camera flash like that, you can actually test it out. You don't need to have a camera, you just have the flash and there's a button on there. Put batteries in there, charge it up, press a button, and you'll see a light flash. That's another application. Inductors are again used for filtering. Inductors and capacitors together are used for passive filters. One of the other most common applications is in two-way speakers like these. So no matter what kind of speaker you have, whether it's like a big, medium size, this one, or like a small one, but if it has two speakers, like a bigger woofer and a smaller tweeter, you have an inductor and a capacitor in there. It uses to filter out. So based on the frequency response, based on the frequency of the incoming signals, the capacitor and inductor filters out or bypasses high and low frequencies and allows low frequencies to go to the bigger speaker and high frequencies to go to the smaller speaker. So those are the real life applications for capacitors and inductors. And then, of course, inside all of these devices on circuit boards, we have capacitors everywhere. But yeah, touchscreens and speakers, and then power supplies. These are the three most common applications of capacitors and inductors. I'm glad you asked that question. Okay, so coming back to the technical side of this. So we have this kind of curve for charging and this one for discharging. And this, again, as I said, is pretty standard. No matter the circuit, no matter the component, no matter the size of the source, no matter the size of the capacitor or inductor, it applies equally to all. Okay, and hence we can say, or not we can say, we can describe all of this by one single equation. That single equation is here. X of t, and again, it's a function of time. That X could be voltage, it could be current, either V or I. If you're trying to describe it for an inductor, we talk in terms of current. So I for capacitor in terms of V, the voltage. So X of t could represent V of t, or it could represent I of t. And then you have the other two terms, F. So it's F. The F stands for final. And the 0 is for initial. In some books, instead of 0, you would see I. So instead of XF or X0, you would see XI. I simply means, again, the same thing, the initial value. Okay. 0 in this case is basically the point at which we begin analysis, in the starting point. And this equation is used for both charging as well as discharging. So XF and X0 can take different values. And then we have e raised to minus t over tau. T is the variable. Okay, it does not have any fixed value. T is the variable. It does not have any fixed value. Tau, again, this is the Greek letter tau. It stands for the time constant. Time constant basically describes how fast or slow is charging, basically describing the amount of time it takes for it to charge or discharge. And that's what the time constant is. It basically depends on the value of the components present in the circuit. For a capacitive circuit, it is the product of resistor and the capacitor, R and C. And for a inductor, it is L over R. Okay, so these are pretty standard. You don't have to memorize any of this, but you definitely do have to understand this in order to apply it. Okay, so there's only three things in here: XF, X0, and tau. That's it. XF, X0, and tau. And then I'll talk a little bit about both charging as well as discharging phase. Don't worry about anything on the right for now. Let me all right. Okay, so here's how it works for discharging. Natural or discharging. For a natural or discharging response, automatically you should recall that the system, not the system, the component is charged. It has some stored energy. It is now releasing or discharging that energy. So when it's releasing, the final value is always 0. Okay, so in a natural response or discharging response, the final value is always 0. Now it could be that the discharging phase could be interrupted before it reaches 0. But when we write down our equations and we begin to solve this, it is always 0. Okay, so we always put the final value as 0. So the final value is 0. The equation simply reduces to x0 times e raised to minus t over tau. And x0 will refer to the initial or stored energy. Okay, so x0 is the initial or the stored energy. Xf is final value, which is 0. If we take the example of the camera flash, the initial or stored energy is provided from the 4 batteries. So depending on how long it takes to charge and how the system is designed, it has certain amount of energy stored into that capacitor or into that system, right? That storage system. And once we click that shutter button, it's sending that signal to that circuitry that you have to release all of that charge. Now, when it releases the charge to the light bulb, depending on the circuit designer, depending on the application, they calculate how bright of a flash do we need. Then what kind of specifications do we need for that light bulb? And then how long it's going to discharge. And then here, T, we can calculate what that voltage or current would be at any given point in time. So time constant tau simply tells us how fast, how quickly it's going to discharge. If we make the resistance smaller, then the energy can be discharged faster. If the resistance is large, then the discharge is very slow. Okay, so in a circuit, if we have a energy source, okay, since we're talking about discharging, let's do it this way. Whether we have a capacitor, inductor or capacitor that is charged, and it is releasing its energy to a load, this R will determine how fast or slow it moves. Okay. So the analogy I like to use is, we think of the inductor or capacitor as a bucket. Okay. You're trying to fill water in this bucket. There is a pipe that is bringing that water to our home, and we're trying to fill this bucket, this pipe, and of course the tap. So the load, sorry, not the load, the capacitor or the inductor is the bucket. So the size of the bucket dictates how fast or slow it's going to fill up, right? The smaller the bucket, if it's the size of a small cup, you can fill it up much faster. However, the capacity is much small. If it's a larger bucket or a larger container, it's going to take a long time for it to fill up, but it can store a large amount of water. Then you have the pipe and the tap. Depending on the flow that's coming through, and depending on the size of the tap, flow could be fast, flow could be slow. And that constriction in the pipe or the size of the pipe is basically the resistance. Of course, the mechanical and electrical analogy is the opposite. The larger the resistance, the smaller the current. And in a mechanical pipe, the bigger the pipe, the more fluid can flow through. Right? So electrical analogy is the exact opposite. The mechanical analogy or a fluid flow analogy, the bigger the pipe, the faster it can flow through. The larger the resistance, the smaller the current. And so it's exactly the opposite. Am I making sense? Right? And so again, so it depends on the size of the bucket, depends on the size of the pipe, and depends on the rate of flow of that fluid or the rate of flow of the water. Now, when it comes time to empty the bucket, just imagine if it's instead of a bucket, let's say it's a water jug, and we have a tap at the bottom of the water jug, right? So how long it takes to empty out that stored container, again, depends on the size of the tap and size of the opening. So that directly relates to this resistance right here. If the size of the bucket is large, meaning the stored energy in the capacitor or inductor is large, then it takes it longer to discharge. If the stored energy is small and the size of the resistor is small, it's going to discharge very quickly. Okay. Let's take a pause, think about that, and let me know if you have any questions. Yes. Yes. So the yes. Yeah. The question being asked is about the analogy between inductor, capacitor, and a bucket. Um, so yes, inductor and capacitor. In this analogy, we are saying that the inductor or the capacitor is a bucket or is a container, right? Bucket or a container or water jug, whatever. It's something to store water, something to store fluid. And that's what we're doing. If it's a small cup or a small mug, we can fill it up faster. If it's a medium-sized bucket, it takes a while. If it's a big tank, it's going to take a long time, right? And yeah, that's what it is. It takes a long time for it to discharge. So in this natural response or discharging response, we have a stored energy. And the stored energy is going to be our X0. X0 is the initial voltage or current that is stored in the inductor or the capacitor. By the way, this discussion applies equally to an inductor as well as the capacitor. Okay, so if I talk about inductors, it applies to a capacitor. If I talk about capacitors, it applies to an inductor also. Okay, it applies equally to both. They're both very similar components. They're exactly the same in many respects, but they're also opposite in many respects. Okay. So this equation again is reduced to this if we are talking about natural or discharging response. Okay. If it's charging, or step response, then XF the final value is typically the source voltage or current. X0 could be 0 or could be any other value. Okay. So if it's completely discharged, then there's no value, there is no stored energy. But if it has some residual energy from the previous step, then X0 would be provided in the problem statement. So it could be 0, it could be any other value. And I can explain that with an example. So this is not part of this class. If you're taking EE 321 after this class, then we study rectifier circuits in there. Rectifier circuits convert AC to DC. which is present inside every laptop adapter, charger, every device. It's built in. Okay. The world runs on DC, but AC power generation and transmission is all in AC. So AC to DC conversion is present inside every single equipment that we use, whether it's a projector, whether it's a monitor, this writing tablet, computer, your laptop chargers, adapters, mobile phone chargers, they all have rectifier circuits in there. One of the primary components inside a rectifier circuit is a capacitor. So the capacitor, what it does is, let me draw in blue. Capacitor charges up and then it slowly discharges and then charges up again and it discharges and it charges up again and it discharges. So there's a charging and discharging in the capacitor going on, right? So this is VC, capacitor voltage VC. So, and this is known as the filtering capacitor. Okay. This is the charging portion. And this is the discharging. This is the discharging. This portion here, where it's going up, is charging. And when it's going down, it's discharging. In this example, let's say this is 0, and I'm trying to analyze the circuit or this response. Let's say this is 0 to 1 milliseconds, 2 milliseconds, 3 milliseconds. Okay. This is a rectified sine wave, and I'm applying a filtering capacitor at the output. So what happens? Capacitor is initially completely devoid of charge. So between the periods of 0 and 1, time period is between 0 and 1, capacitor is fully discharged, no stored energy. Right? Now you flip the switch on, power is applied to the system. Within 1 milliseconds or half a millisecond, let's say it reaches full charge. So for the first time period, if I had to write a transient response or an equation for the transient response, I would say X0 is 0 volts. My XF or final value, let's say whatever this number is, let's just say 5 volts, random number, okay? My XF would be 5 volts. Then when the input starts going down, the capacitor begins discharging. Now, this discharge portion is being supplied. The capacitor has stored the energy, so it's now supplying that stored energy to the output. So at the time the input is actually going down, the output still receives the energy from the capacitor. Okay, so all of this portion is the stored energy that is provided to the output from the capacitor. Okay, so if I was to write this again for the time period 1 to 2, now let's say my capacitor discharged to 4.8 volts. If I was to write an expression for 1 to 2, actually, I shouldn't be doing 1 to 2. I should be doing, this is 0.5. So let's do 0.5 is the charging, and 0.5 to 1, where my capacitor is discharging. So from 0.5 to 1, my capacitor is discharging. So, it has some stored energy. my X0, my initial value would be 5 volts. My final value would be 0 volts, even though it will never reach 0. This is not something that we are going to do in 201. This is something we do in circuits for EE majors. But I'm letting you know, this is an important concept. When we perform this analysis and we break it down into different time periods, if you are looking at the discharging portion, the final value is always, always, always taken as 0 volts, even though it is going to be interrupted right here. Does everybody see what I'm saying? The capacitor is discharging, and eventually sometime in the future, it's going to reach 0 volts. So if I'm trying to describe an equation for the discharging portion, final value is always 0 volts. This will be interrupted right around here. I don't know what the time would be. It wouldn't be 1.5, it would be less than 1.5. It gets interrupted and it starts charging again. And for that portion, let's call this, I don't know, 1.4, right? So 1.4 to charging to 1.5, my capacitor has stored energy. So my X0 initial energy in this charging portion is 4.8. My final value is 5 volts. And that's the difference between these two cycles. They are both charging and they're both charging cycles, but the first one, it does not have any stored energy. So starting value is 0, ending value is 5. Second charging portion, stored energy is present. So X0 starting point is 4.8. My final value is still 5. In the discharging portion, it does not matter. You take the stored energy as your starting point, 5 volts. End point is always 0. It does not matter that it's going to get interrupted. Final value is always taken as 0. This applies equally to a capacitor as well as a inductor. Okay, I hope this clears up concepts because we are out of time. In addition to this slide, I'm going to just leave you with this. In addition to this slide, which is lecture 17 from today, do read up on page 20 in the annotated notes in chapter 4. And this is all in the class notebook. It's available to all students. And then in my lecture videos, there's a corresponding talk about what this means. Okay. So do read up about this and bring your questions to class on Friday. Clear up any of the questions you might have, and we'll look over the homework 14. And then after that, we begin AC analysis, which is going to get, well, even more complex. All right, we'll end class here today, and we'll see you all on Friday.